Hi class, today we're going to start a new chapter. It's chapter 10 and we're going to start on 10.1, which is on systems of linear equations in two variables. Okay, so we're going to look at a system of linear equations and their solutions. So a system of equations is a set of equations that involve the same variables. Like x or y or a and b, t and s. Those are our variables. And then a set of linear equations that'll look like equations of the form ax plus by equaling like some k, where a, b, and k are numbers. They're constant, so they will not change, but x and y are variables. So that is what we will plug in values into. Okay, so for example, we can have something like this. So these kind of curly brackets, those are often used to define a set. So I'll be drawing these a lot. So it's a set of equations. So we have 2x minus y equals 5 and x plus 4y equals 7. So you see we have these linear equations because there's just an x and a y. They're not multiplied together. They're not squared. They're just nice lines. And then we can call this one equation 1. And the second one equation 2. And now we can check that x equals 3 and y equals 1 is a solution. So if we plug in those values, we will see that 2 times 3 minus 1, that is 6 minus 1, that equals 5. That matches equation 1. And then if we look at 3 plus, 4 times 1, this is 3 plus 4, which equals 7, which matches equation 2. We can also write the solution. Three, 1, where our 3 corresponds to x and our 1 corresponds to y. Just like if you were to graph a point, that being said, we can graph these two lines or these two functions. So if we were to take our first line, which might look something like this, that's fine. This would be 4y plus x equals 7. And then if we took another line and we did something like this, where this is 2x minus y equals 5, then this point here where they intersect, that is our point 3, 1. So another way to interpret this is the solution to a system of linear equations is the point where they intersect. Okay, and then we're going to learn some methods to solve. So our first method is the substitution method. So the first step in the substitution method is going to be solve for one variable. Two is going to be substitute. What this means is we're going to substitute the one variable that we solved for above into the second equation. And solve for the second variable. I'm just going to put var for variable. I'm going to underline some things too. Okay, and then our third step is we're going to back substitute. So what this means is the value from the second equation that we solved for in step 2, we're going to plug that back in first equation. So we're going to solve for that variable we isolated in the first step. So what this looks like is, if we look at an example, let's take the system. 2x plus y equals 1 and 3x plus 4y equals 14. So our first step, we're going to take 2x plus y equals 1. And solving for y, we're going to have that is 1 minus 2x. Okay, so then in step 2, we're going to plug this value in for y. So we're going to have 2x plus, we plug it down in here, 1 minus, oh, so sorry, there needs to be, I did this backwards. I was plugging into the original equation we have. We need to plug it into the second equation. So what that means is we're going to take our 3x plus 4, and now we're going to plug this in for y. 1 minus 2x equals 14. Then rewriting, we get a 4 minus 8x equals 14. Subtract 4 from both sides and combine the 3x and the negative 8x. We end up with a negative 5x equals 10. And if we divide both sides by negative 5, we end up with x equals negative 2. And now we're going to back substitute. So we're going to take this x and we're going to plug it into our original equation. So we're going to have 2 times negative 2 plus y equals 1, which becomes negative 4 plus y equals 1. Adding 4 to both sides, we end up with y equals 5. So our solution is negative 2, 5. And then graphically, this will look like, if I do something like this. And this. Very nice. Okay. Where this line here, the blue line, is 3x plus 4y equals 14. And this line here, the red line, is 2x plus y equals 1. And then this intersection point here, this is -2, 5. Okay, and then our second method that we're going to learn about is elimination. So our first step is we're going to adjust coefficients. And so we're going to multiply one or more of our equations so that the coefficients of one or more, of one or more variables, and the equation is the negative of its coefficient in the other equation. So, for example, that would be like if we had 6x plus y equals, 13, and 5x minus y equals 7. So you see here how we have a positive and then we have a negative. So if you were to add these two equations together, those would cancel. And that's exactly what we're going to do in our second step, is we're going to add equations. And then we're going to solve for remaining variable. And then we're going to back substitute again, just like in the first method. Okay, so if we were to look at an example of this, if we take our system as 3x plus 2y equals 12 and 4x minus 2y equals 2. Our first step already done. We have a positive 2y and a negative 2y, so those will cancel. So now we are going to do that. We're going to have 3x plus 2y equals 12 plus 4x minus 2y equals 2. Adding these together, we end up with a 7x plus 0y equals 14. So solving, that will give us an x equals 2. And now doing step 3, I'm going to plug it into the first equation. So we're going to have a 3 times 2 plus a 2y equals 12. So then we get a 6 plus 2y equals 12. If we subtract 6 from both sides, we get a 2y equals 6. Divided by 2, we get y equals 3. So our solution is 2, 3. Okay, so there's this next part of lecture is very important. It is the number of solutions of a linear system in two variables. So, for a system of linear equations in two variables, exactly one of the following is true. So the first one, the system has exactly one solution. 2, the system has no solution. Or 3, the system has infinitely many Okay, so what this means is if we were to look at the graphs of problems like this, for the first one, we would have something like this. Where the two lines would intersect, there would be exactly one solution. Or we would have something like this. Where our lines are parallel. And do not intersect. So you can see these lines, they will never touch because their slopes are parallel. Or we have a third option. Oops. And this is when the lines are, it's kind of hard to see. The lines are the same. Oops. Go inside. I.e. they're the same line. So here, at every single point of the line, they are the same. So there's an infinite number of points where they're exactly the same because the lines are just the same. So this is when we have two variables. That's very important here. Because that means we're looking at lines on graphs. Okay, so now we're going to run through some examples of each type of problem. So for our first example, we're going to look at the system 3x minus y equals 0 and 5x plus 2y equals 22. And I'm going to do both methods of solving so you can see another example. So first, we're going to look at substitution. So I'm going to solve for y in the first equation. So we're going to see that y equals 3x. And so then I'm going to plug it into the second equation. So we're going to have 5x plus 2, 3x equals 22. So we're going to end up with 5x plus 6x equals 22, which is 11x equals 22. So that means that x equals 2. And now back substituting in, we're going to plug this into the first equation. So we're going to have y equals 3 times 2, which gives us y equals 6. So our solution is 2, 6. And now doing the second method, if we do elimination, so our first step is we're going to multiply the first equation by 2. And leave the second equation the same. And the reason we picked multiplying by 2 is we want these terms here to cancel. And I thought this one would be the easiest because we just had to multiply 1 by 2. If we wanted the x's to cancel, we would have needed to multiply the top equation by 5 and the bottom equation by -3. And that's just a lot more work. This one's a little simpler. So then rewriting, we get a 6x minus 2y equals 0, and a 5x plus 2y equals 22. So if we add them together, we get an 11x plus 0y equals 22, which leads us to x equals 2 again for when we divide by 11. And then back substituting, so this was step 1, this was step 2. Now back substituting, we end up with, and you can pick either equation to work with. I'm going to pick the first one. So we're going to have a 3 times 2 minus y equals 0, which leads us to 6 minus y equals 0, which leads us to y equals 6. Because we could have just added a y to each side to solve for it. So again, our solution is 2, 6, which matches the way we did it up above, which makes sense. They should give us the same answer, 2, 6, 2, 6. All right, so now we're going to do a second example. Oh, and I was supposed to stress in this first example, you see there's only one solution. The only solution is when x equals 2 and y equals 6. Okay, so here for our next example, we're going to look at the set 8x minus 2y equals 5 and negative 12x plus 3y equals 7. So here I'm going to just use elimination. So we're going to multiply the top equation by 3 and the bottom equation by 2. So we're going to have 3, 8x minus 2y equals 5, and 2, negative 12x plus 3y equals 7. And the reason we're doing that is because of this 2 and 3 and the y. We're going to multiply to get them both to be 6. Or negative 6 and 6, so that they cancel easier. So this becomes 24x minus 6y equals 15, and negative 24x plus 6y equals 14. Well, you'll see here, if we add these together, we get 0x plus 0y equals 29. Well, this 0 does not equal 29. That's wrong. So therefore, there is no solution. And this should make sense because you'll see here that these equations are pretty similar to each other. We have a 2 and an 8 and a 3 and a 12. Well, this would be the same as 4x minus y. And then if we divided this one by 3, this would also be a 4x minus y. So we see that their slopes are similar. So that means that we would need to just make sure that their outputs are the same thing. But since they're not, then there's no solution. Okay. So looking at one final example from this part, we're going to look at 3x minus 6y equals 15 and 4x minus 8y equals 20. So we're going to multiply the first equation by 4. And the second equation by 3. And this will give us a 12x minus 24y equals 60 and a 12x minus 24y equals 60. Well, there we go. These are the exact same. These are the exact same equations. So that means that we're going to have infinite solutions, but we do need to solve for the line that satisfies this equation. So I'm going to just grab the first equation to work with. So if we have a 3x minus 6y equals 15, well, if I divide everything by 3, this will give us a x minus 2y equals 5. And then I like to solve it in the y equals like mx plus b form. That's my favorite. So we're going to subtract an x from both sides. So we're going to have a negative 2y equals 5 minus x. We're going to divide both sides by negative 2. There we go. Sorry, that got a little messy here with the 5. So this is our line, but we don't want to leave it with x and y because those are the variables that we used in our system. We want to choose a new variable, and the normal one to pick for something like this is t. So we're going to pick, and just like let x equal t for this. So we'll have 1/2 t minus 5/2 is a solution for all t in the real numbers. That's what this fancy r is for again. We also could have written all t in the interval negative infinity to infinity. So this means that if we pick any t in the real numbers and plug it in to this equation here, that will satisfy our equation. We also can write it as t and 1/2 t minus 5/2. This is another way to write the solution. Okay, so now we're going to move on to an application of this, which is modeling with linear systems. So first we're going to go over some guidelines. So we're going to go over guidelines for modeling with systems of equations. So our first step is going to be identifying the variables. So we're going to identify the quantities that the problem asks you to find. And we're going to introduce a notation here. And it's typically X and Y, because those are just the ways we're most used to seeing equations written out is with X and Y. So our brain's just a little better at looking at equations and knowing how to solve those. Our second step is going to be to express all unknowns in terms of our variables. So we're going to read the problem again. To find relationships, so what this means is this step is where we set up our system. And then our third step, we're going to solve and interpret. So we need to state our final answer as a sentence that answers the posed question. Basically, this sentence needs to let the reader know, the reader's usually going to be me in this class because I'm your grader as well, but you need to state it in a way that I can understand your results without even having read the problem statement. I shouldn't have to look at your work to understand what's happening. You should be able to say like exactly in one nice sentence at the end what this means. And I'll give you an example of this as we run through a practice problem. But you need to write a sentence. It's very important. That's going to, because it's the bulk of your work. If you just write like 80 pounds and I don't know what that means you didn't do a good job of solving the equation. You got to give context to your solutions. So we're going to look at an example of a distance, speed, time problem. So these are often going to be posed as word questions. So a woman rows a boat upstream from one point on a river to another point that is 4 miles away. Rowing upstream, she does it in 1.5 hours. The return trip traveling with the current, so downstream, that takes 45 minutes. All right, so the question is, how fast does she row relative to the water and at what speed is the current flowing? So the first part of this problem, we need to identify our variables. We are asked to find the woman's speed. We're also asked to find the speed of the current. So that means that this is going to be our x and y, and x is going to be the rowing speed, miles per hour, and y is going to be the current speed, also miles per hour. Okay, so now that we know what the question is asking us, we need to create a system or a bunch of equations to set up our system. So this is going to be express unknowns in terms of variables. So I'm going to create a little table. It's going to be words versus our algebra. So we already know that our row speed is represented by an x, and our current speed is represented by a y. So we need to know how fast she rows upstream, her upstream speed. Well, that's going to be how fast the woman rows fighting the current. So we're going to subtract the current speed. Versus when she returns downstream, it's going to be how fast the woman rows plus the current speed because she's traveling with the current. So now we need to set up our system. I forgot which number was setup system. It's still within number 2. So we're going to set up system. So it tells us up here that our distance is 4 miles. And 1.5, that's upstream. Versus 45 minutes, that's downstream. So to set up our system, we're going to have our speed upstream times the time upstream. That's going to equal our distance. And then our speed downstream times our time downstream. That's also going to give us the same distance. Because distance is measured by speed times time. So for our first equation, speed upstream, that is going to be represented by this equation. So we're going to have an x minus y times the time upstream. Time upstream was 1.5 hours. So that's going to be represented by 3 halves, and this equals 4. And then for our second equation, our time downstream is this, our x plus y. And then 45 minutes, that's 3/4 of an hour. And then I'm going to rewrite this in a better way. So I'm going to multiply both sides by 2, and then for the first equation, and then distribute the 3. So we're going to get a 3x minus 3y equals 8. So we can cancel the fraction. And then we're going to do a similar thing for the second equation. We're going to multiply by 4, and then we're going to distribute the 3. So we get a 3x plus 3y equals 16. Well, now we see here we're all set up for an elimination problem. So we're going to take our 3x minus 3y equals 8 and our 3x plus 3y equals 16, and we're going to add them together. We're going to end up with a 6x equals a 24. So that will give us x equals 4. We divide by 6 on both sides. And then now we're going to back substitute in with this x equals 4. And I'm just going to plug it into the first equation. So we're going to get a 3 times 4 minus 3y equals 8. So a 12 minus 3y equals 8. We're going to subtract 12 from both sides, and we get a 3y equals negative 4. And if we divide both sides by negative 3, we get a y equals 4/3. Okay, so now we need to write it as a sentence. So the woman rose at a speed of 4 miles an hour, and the current flows at a speed of 4/3 mile per hour, which is the same as an hour 20. That's fully wrong. This is miles per hour. I was thinking in 1 hour you can get where you need to get to. It's unimportant. We're going to leave it like this. I'm sorry to confuse y'all. So here's our sentence. So now we know, without having to look at any of the work, how fast the woman can row and how fast the current is moving. Okay. So we're going to look at one other example of this type. I'm going to move a little bit faster now that I've broken down the steps kind of slower. And this is a mixture problem. So a vintner, I'm sure there's a French way to say this word. It fortifies wine that contains 10% alcohol by adding a 70% alcohol or alcoholic solution to it. The resulting wine has an alcohol strength of 16% and fills a 1,000, or sorry, it fills 1,001 liter bottles. How many liters of the wine and of the alcohol solution does the vintner use? So our first problem is going to be identifying the variables. So looking at the problem, it's asking us how many liters of wine and of the solution does the vintner use? So that means that X is going to be the amount of wine measured in liters, and Y is going to be the amount of solution. Okay, so then our second step is going to be to express the unknown quantities. So we're going to do a similar thing with our table. And again, we already know amount of wine is going to be represented by X. Amount of solution is going to be measured by Y. And then we know the alc percentage in wine. We know that this is 10%. So 0.10 of the wine is alcohol. Similarly, the alc percentage in the solution, this is 70%. And we got that from up here, our 10% alcohol and our 70% alcohol. This lets us know what our values are going to be, our percentages of wine. So now we need to set up our equation. So we know that by adding our wine and our solution, we end up with 1,000 liters of wine because we can fill 1,000 1-liter bottles. Similarly, we know that if we were to add 10% of that, if 10% of the wine is alcoholic and 70% of the solution is alcoholic, we need to end up with 16% of the total amount, which is 1,000, to also be alcoholic. So here we're going to simplify this second equation by multiplying by 10. So we can rewrite this one as X plus 7Y equals 160. Oh, sorry, 16,000. This number here is 160. But since we multiplied by 10, we end up with 1,600. So now we have our solution, or our system, as X plus Y equals 1,000, and X plus 7Y is 1,600. So if we subtract this first equation from the second, so similarly we could rewrite it as negative X minus Y is negative 1,000. X plus 7Y is 1,600. And we add them, we end up with 0x plus 6y equals 600. So our y equals 100. And then if we back substitute, where we plug this 100 into the first equation, we get x plus 100 equals 1,000. And then subtracting by both sides, we get x equals 900. So our solution is 900, 100. And then for our sentence, the vintner uses 900 liters of wine and 100 liters of alcohol solution to fortify the wine. There we go. So that's the end of section 10.1. Thanks, class.